Okay, for number 6, we have a cobalt complex, and its charge is balanced by sodium ions represented outside of the brackets here. And so to start this problem, I'm going to first dissociate away those sodium ions. And so each one has a positive charge, and so that means our complex will be left with a -2 charge. Okay, and so once we have our complex isolated, we can figure out the coordination number by looking at the ligands stuck in the brackets with our metal. And so En is a neutral bidentate ligand, so it's contributing a coordination number of 2, and we just have one of them. And then each chloride has a coordination number of just 1, and we have 4 of them, so overall we have a coordination number of 4 coming from all of those chlorides. And so the overall coordination number is going to be 6 for this complex. And then to figure out the charge in the cobalt, we're instead going to look at the charge on each of those ligands. So En, it's made up of some carbons and some amines, and it's going to be neutral. And so this will have a charge of 0. And we know each chloride is going to be -1, so overall those will contribute -4. And so to make this overall charge -2, the cobalt is going to have to be +2, making B the correct answer. In number 7, we have this redox reaction with nitnium. And we have the whole reaction, and they want us to figure out which is the reducing agent. And so we know the reducing agent is going to be whatever gets oxidized. And so to keep track of how the electrons are moving around, we'll assign oxidation numbers. And we can see that the nitnium is changing from +3 to 0. And those were easy to keep track because they're just on their own. And then for the manganese compounds, I've assigned the oxygens -2, and then made the manganese charges, or oxidation states, whatever would need to be to get the overall charge on the molecule straight. So for this MnO2, the oxygens would be contributing an overall -4. The molecule is neutral, so the manganese would have to be +4. For the MnO4-, each oxygen would be contributing -2, making the overall contribution -8. The molecule has a -1 charge, so the manganese would be +7. So we can see that the nitnium reaction here, we can watch it's going from an oxidation number of +3 to 0. So it must be gaining electrons to become more negative. So this is being reduced. The manganese is changing from +4 to +7. So it's becoming more positive. So that must be getting oxidized and losing electrons. And that reaction is written here. And so, since manganese oxide has the manganese in the reactant that's changing oxidation states to become more positive, that will be our reducing agent. For number 8, we're trying to decide which has a central transition metal that has 7 electrons in its 3D subshell. And so what I've done here is use the periodic table to figure out how many electrons are present in the neutral species of whatever transition metal is present here. And then I've also written if the transition metal will be an ion or not. And then we'll adjust for that when we look at the electron configuration. So manganese is just our neutral metal. And we have 7 electrons that we need to draw in. So we have our argon core, and then we have 1, 2, 3, 4, 5, 6, 7 electrons. And we're just drawing for neutral manganese. So this would be the configuration, and we would have 5 d electrons. So that's not the correct answer. So now we can look for cobalt, which will also have an argon core. And in this case, it's going to be cobalt 2+, because each of those chlorides has a -1 charge. So I'm going to start by writing the configuration for neutral cobalt. We have 9 electrons to draw. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so, because we have cobalt 2+, we're going to have to get rid of 2 electrons. And so to do that, we're going to erase the electrons in the 4s subshell. And so then after we do that, we're left with 7 3d electrons, making this the correct answer. And so just to be sure, let's go ahead and write the configurations for the other 3 answer choices. So we have in the next one, iron carbon monoxide complex. So carbon monoxide is neutral, and so the iron in that complex will also just be neutral, because there's an overall charge of 0 on the entire complex. And if you look at iron, after its argon shell, we have 8 electrons to draw in. So we'll have 1, 2, 3, 4, 5, 6, 7, 8. And so that would be its configuration, and we would end up with 6 d electrons. So that would not be the answer. And then in this next copper complex, we have water as our ligand, and water is of course neutral. And so that +2 charge on the whole complex would be coming from copper. So we'll need to figure out copper 2+. We're going to start by drawing neutral copper. And it has 11 electrons after its argon core. And this is one of our exceptions. So what we're going to do is only have 1 electron in the 4s. And instead we're going to completely fill the 3d. So this is an exception, and the other metal that's similar to this is chromium, where we end up with 1 electron in the 4s, and then we half fill the 3d subshell. Okay, so then if we want to make this copper 2+, we need to erase 2 electrons still. So we're going to erase the 4s electron and then one of these paired electrons. And then we can see we'll have 9 electrons in the 3d. So that would be false. And then finally, we can look at nickel. And so nickel hydroxide, the nickel will have a +1 charge. And nickel has 10 electrons after its argon core. We can draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then to make it nickel 1+, we will just erase one of those 4s electrons. And then we're left with 8 3d electrons. Okay, so we can see that B is the correct answer. In number 9, they want us to compare the strengths of some carboxylic acids. So these are all going to be weak, and the proton that dissociate away are the ones attached to the oxygen in that carboxylic acid group. And the reason this is the hydrogen that would leave is because this bond is really polar. The oxygen and the carboxylic acids are doing a good job of pulling electron density away from the hydrogen. So it's more likely to leave as H+. And if we add more electronegative groups to this and further pull electrons away from the hydrogen, it's more likely to leave, and it's a stronger acid relatively. So in the case of answer choice 2 here, we have 3 halogens on here, 3 chlorides, pretty electronegative, pulling electron density further away from the hydrogen. And so this would be the strongest of these acids. Whereas in answer choice 3, there's no halogens attached. We just have hydrogens around that ring. And so it's going to be the weakest option. And then between 4 and 1, we have 2 halogens on each one. But this chlorine is going to be more electronegative than the bromine. And so it will do a better job pulling electrons away. And so that would be the next strongest, followed by that choice with bromines. And so option choice B is correct. For number 10, we have this graph where we're watching uranium decay and seeing those steps. And they want us to figure out how many alpha particles are being emitted in this process. And so we know alpha decay is when we lose 2 protons and 2 neutrons, and we lose a total mass number of 4. And we have mass on the x-axis and protons on the y. And I think it's easiest to look at the protons and see how, like in this first step, we've gone down by 2 protons, as would happen in an alpha decay. And so then we can just kind of count these steps down. So we'd have 1, 2, 3, 4, 5, 6, 7, 8. And we can also see how the mass number changes by 4 as this is happening. So we'd have 8 alpha decays. In number 11, I want us to figure out the bond order and whether cyanide is magnetic. And they told us to use the large interaction diagram, so I've drawn that on the right here. That's on the data sheet. So to figure this out, we need to figure out how many electrons are involved in the bonding. And so carbon has 4 valence electrons, nitrogen has 5, and because of that negative charge, there's 1 more extra electron, for a total of 10 valence electrons involved in the bonding. And so when you're just using the valence electrons, we're going to start on the 2s. And then we can fill in our 10 electrons. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and so once you fill in the diagram, it's really easy to figure out the para or diamagnetic. So paramagnetic is when we have unpaired electrons. And diamagnetic is when we don't. And so we can see in our diagram that we don't have any unpaired electrons. So it's going to be diamagnetic. And this would not interact with a magnet. Think of it, the magnetism dying. And then to figure out the bond order, we're going to use this equation where we take the number of bonding orbital electrons, subtract the anti-bonding electrons, which are denoted with this asterisk, and divide that number by 2, because there's 2 electrons in one bond. And so the only anti-bonding electrons that we filled in are here in the sigma star 2s orbital. And then the other 8 are in bonding orbitals. So we can go ahead and say that we'd have 8 bonding electrons minus 2 anti-bonding divided by 2. We have 6 divided by 2, so our bond order would just be 3. So answer choice D would be correct here. Okay. And number 12, trying to figure out how many unpaired electrons there are in the copper ion, or the copper atom in this complex ion. So I'm going to start by separating the complex from the ions used to balance the charge, so that's going to be the things outside the brackets, or the sodium. So we have 3 sodium ions, and when those dissociate away, we have our copper complex, still with the cyanide, that would now have a -3 charge. Okay, so then we have to figure out the charge on the copper so we know how many electrons to keep track of. Cyanide, each one has a -1 charge, so these would be contributing an overall -4. And so that means our copper would have to be +1. Okay, so to start, I'm going to draw the configuration for just copper neutral first. So we have our argon core. We have 1 electron in the 4s because it's copper and it's one of our exceptions. And then I'll have 10 electrons in the 3d. And then to make it copper plus, I'm going to erase an electron and I'm going to erase the 4s electron. Okay, so I have 10 electrons to put into my diagram. And they say it's a strong field ligand. So we're going to have a low spin. And so when I fill this in, I can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so then we can see we have 0 unpaired electrons. In number 13, there have a bunch of cobalt complexes. It's just they've changed what ligand are attached to the cobalt. You can see that we have different colors that the complexes appear. And so whatever complex, or whatever color the complexes appear, it's going to be the opposite of what they've absorbed. And so you can look at the color wheel, and whatever is opposite the color that they appear is going to be the color that they've absorbed. And so I've written those absorbed colors here. And the colors are important because they can tell us about the wavelength and the energy of that light that's being absorbed. And so we know that violet or more purple light has a shorter wavelength and higher energy than red light, which has a longer wavelength and lower energy. So then we can think about what it means to be strong field versus weak field. And so for a weak field ligand, this energy difference between the types of d orbitals, or the crystal field splitting parameter, is going to be small. The ligand isn't strong enough to pull those energy levels apart. But if we have instead a strong field ligand, this energy difference will be much bigger. And so whichever one is absorbing the highest energy photon will have the greatest splitting and will be the strongest. Okay. So we can say the cyanide, since it's absorbing the highest energy photon, has the strongest field strength, followed by the ammonia, followed by the water, and then ending with the chloride. Making E the correct answer.